Welcome everyone to the colloquium. Today's speaker is Dr. Sanjeev Tiwari, who will be speaking on dependence of heating in coronal loops and plumes on the coalescence and polarity mixture of magnetic flux at their feet. Sanjeev Tiwari completed his PhD from Physical Research Laboratory, Udaipur Solar Observatory, India, on helicity of the solar magnetic field. He is the recipient of Justice Oak Best PhD Thesis Award of the year 2010, given by Astronomical Society of India. Dr. Tiwari worked as a postdoctoral fellow at MPS, Germany from 2011 to 2013. He then joined NASA MSFC as an NPP fellow, where he was also appointed as a research scientist at University of Alabama, Huntsville. Dr. Tiwari is an adjunct graduate faculty at CSPAR, University of Alabama, Huntsville, and has mentored more than 15 students, including undergraduate, postgraduate, graduate students, on various research topics. Since June 2017, Dr. Tiwari has been appointed as a senior research scientist at LMSAL Baeri in Palo Alto. He is currently a member of operations and/or science teams of solar missions Hinode SOT, IRIS, HICE, and upcoming MUSE. So to Sanjeev now, please start.
Thank you very much, Mausumi, for the introduction and also for inviting to give this talk. Here is a list of my collaborators, and also these are some students who have contributed to one or the other research topics that I will be talking about today. I will start with coronal loop heating and then switch to plume heating at the later part of my presentation. When we compare solar X-ray and UV corona with the surface magnetic field of the sun, we can steadily notice that the concentrations of intensity enhancement in the corona directly corresponds to the magnetic field concentrations on the surface of the sun. The active region with the strongest magnetic field, for example, here, this one, is brightest. This suggests that there is one-to-one correspondence. So stronger the magnetic field, brighter the solar corona is. AIA 94 shows a similar pattern. Again, this is the same active region in continuum intensity image, and this is the biggest active region, and that is brightest. It was consistently quantitatively shown by Ignacio Guerrero et al. That stronger the magnetic field in coronal loops, brighter the loops are. So there is a positive correlation, and this is also well known that the rate of radiation or rate of heating is inversely proportional to the volume of coronal loops, and therefore heating rate is inversely proportional to some order of the length of the loop. Looking at more in the literature, it is found that sunspots are dark on the surface and in the X-ray corona. Sunspot umbra have no or little X-ray and coronal UV emissions. None of the bright coronal loops originate in sunspot umbra, which are somewhat inconsistent with the following. Loops rooted in sunspot umbra are the brightest ones among others. For example, the Peter Focal's this paper, the second sentence here, the brightest loops are associated with the flux tubes leading to the umbra of sunspots. Even in AIA observations, in 94, for example, this one here, it has been found that the hottest and brightest coronal loops actually are rooted in sunspot umbra. Falcone et al. And Moore et al. Found that brightest loops are rooted near neutral lines, and they suggested that the flux cancellation at the feet of the loops might induce loops coronal brightness. From all these observations, some questions come into mind. For example, why sunspots, particularly umbra, are usually dim in coronal UV and X-ray images. And you can easily guess that, okay, sunspots and sunspot umbra particularly has very strong magnetic field, and magnetic forces don't allow convection, and so the heating is not possible in sunspot umbra. But then what is special about some of the loops that stem from an umbra, but they are the active region's brightest coronal loops in UV and X-ray corona at a given time? Are the brightest active region coronal loops always rooted at neutral lines? Does loop's routing pattern, that is magnetic setting on the photosphere, tell us something about its coronal brightness? We try to address these questions, and for that we followed a couple of active regions for more than 24 hours. And these active regions were selected based on the following criteria: that they have developed sunspots in east magnetic polarity, and they are close to the center, and they're non-flaring. Now, before I move on to show you some of the hottest and brightest coronal loops that are rooted in sunspot umbra, penumbra, or nearby area, I would like to point out in very high resolution SOT observations where in a sunspot, if a coronal loop is rooted, where it would be, and how it would be different when a loop is rooted in sunspot umbra or penumbra. So sunspot umbra, if a loop is rooted in sunspot umbra, this dark region or this red one here in magnetic field map or in field inclination map in this blue region, then it is in a non-convective environment. This is the region where convection is strongly suppressed. Whereas if it is rooted in sunspot penumbra, then it has convective environment. How? So sunspot penumbra is formed of two components. One is penumbral filaments, which are elongated magnetized convective cells. You can see all these filaments, they are basically elongated magnetized convective cells. And the second component is the spine field, which are these red pixels in the magnetic field map and blue pixels in the field inclination map. These red here and these blue pixels are basically the same. So these are more vertical magnetic field, and they are outward extension of umbral field. They have similar properties as sunspot umbra, but they are more inclined. So penumbral filaments are convective cells. They cannot reach into corona. They are well below chromosphere and photosphere. And penumbral filament, so any loop that is rooted, that has to be rooted in these spine field regions. So what is difference in a loop that is rooted in umbra and penumbra is that in sunspot umbra, if loop is rooted, it is rooted in a non-convective environment, whereas if loop is rooted in penumbra, that is in a convective environment. It is surrounded by these convective cells, penumbral filaments. Okay, so we look at this movie in these 4 panels. We have line of sight magnetogram 1600, AIN 193, and AIN 94. And we find many bright and intermediate bright loops, particularly looking at iron 18 in AIN 94 because we are interested in hottest loops. So we followed them, and you can see if you look carefully, there are some arrows that point to some of the brightest coronal loops, but movie runs probably quite fast and you may not notice it. I will show you some image frames from this movie to point this out more clearly. So first, summary of what we noticed in this movie is that bright loops are episodic. They have 20 minutes to 2 hours of lifetime. There are repeated subflares, and they are seen in sets of loops with a given routing pattern. The brightest loops are rooted in umbra, penumbra at one of their feet, with their other feet foot point in opposite polarity unipolar class or mixed polarity class or penumbra, and they never end in opposite polarity umbra. The class-to-class loops have only intermediate brightness. They never become as bright as the brightest loops that I will show some examples. AIN 94 images are dim in umbra. So this is one image frame to show that one example of the brightest loop. And this one is rooted in sunspot umbra penumbra boundary, basically. This is in spine field, of course, but this is at umbra penumbra boundary at 1 foot point and near penumbra. So again, I must point out that these contours strictly outline sunspot umbra. So outside this, we have sunspot penumbra, and then you have, of course, whites and closet regions and whites. So this one is rooted in umbra-penumbra boundary at 1 foot point, and in Plaz or penumbra, basically it should be penumbra. It has penumbra-like behavior at the other foot point. We also verified by computing differential emission measure that the brightest loops in AIA 94 are actually hottest. Here there is an example of intermediate bright loop, then you can see fan loops, which are the coolest. This is another example of hottest loops. In that you have the penumbra again. Penumbra or swine field connects to a mixed polarity magnetic flux region here. It goes to negative polarity here, and part of it goes there, and you have mixed polarity or positive polarity flux here. This is another set of hottest loop. This one, particularly that I have marked with arrow, you can see this is connected to sunspot umbra at 1 foot point and in unipolar Plaz region at the other foot point here, this positive flux. These are two examples from another active region that we investigated. So here we have a number 1 loop here. This one is from umbra to Plaz. So this one goes to sunspot umbra, rooted here, and 1 foot point, and the other foot point it is rooted in unipolar Plaz region, this positive flux here. And second one is, again, it is rooted in umbra at 1 foot point, and at the other foot point it is rooted in this positive flux region here, which is next to, there is a negative polarity flux in the close proximity of the sand. I would call that mixed polarity flux. Plaz to Plaz connections. This one, for example, positive to negative. This loop, this never becomes hot loop. This is only intermediate bright loop as compared to the hottest loops that I showed. So there are many Plaz to Plaz connections, and they're always at intermediate temperatures. They never become as bright as the previous ones. Okay. We did not find any of the umbra to umbra connections in any of the active regions and in any of the AIA channels. For this particularly, looking at or searching for umbra to umbra loops, we also looked at different AIA channels. To find out whether there is umbra to umbra loop at all, we extrapolated. We did use Wiegelmann's code to do the extrapolation. And first we verified that the observed loops in AIA 94 match well with the model field lines. We compared them, and when we were satisfied that the observations match well with the modeled field lines, then we looked for umbra to umbra connections. This is one set of loops, and this is about 100 megameters or lower. And then we looked for different heights of those loops. There are different loops at different heights. So we found that there are many, many loops that connect sunspot, let's say field lines. Loops are, I'm using loops for observations and field lines for extrapolated term. So we found many, many field lines in the extrapolation that connect sunspot umbra to umbra of different heights, but none of these field lines matched with any of the observed loops in any AIA channel. That means they are the dimmest loops. They don't have any emission. Well, this is just a fancy way of verifying where the loops are rooted in our field model. So this sketch summarizes these observations I just mentioned. In that, the brightest coronal loops are the ones that are rooted either in umbra or penumbra at 1 foot point, and in penumbra are unipolar Plaz or mixed polarity Plaz at the other foot point. These are, so what is special about these three connections is that they have a strong magnetic field and they have freedom of convection at least at 1 foot point. Now, umbra to umbra connections, whether they are short or long, they are not visible, or they are the dimmest loops because they are frozen basically at both foot points. So there is no convection going on either in this umbra or in this umbra, even though they have the strongest magnetic field. That challenges the idea that the stronger the magnetic field, brighter the solar corona is. Well, so what is special about this loop that is also rooted in umbra Here this says convective freedom, which is important. So this tells that convection is equally important to magnetic field to make a loop bright. And these two are important parameters. If this loop, for example, if it was rooted in sunspot umbra, then right now it is the hottest loop at a given time. When you follow the evolution of the active region, it would be the dimmest loop. Going to class connections, we have these loops never become as bright and hot as these ones, because although they have freedom of convection at both of their foot points, they don't have a strong enough magnetic field as these ones have. You can also extrapolate this to quite some regions. There you have even better convection or more efficient convection, but then you have weaker magnetic field. Therefore, those loops are even dimmer than this one. This one, the big one here, these are fan loops structures, and we know that they have same connection as this penumbra to penumbra, but then we know that these are very long loops, and therefore they are dim, because the radiation is, of course, inversely proportional to the length of the loop, as I mentioned before. Now, if you think about this plot, where you have stronger the magnetic field, brighter the loop is, and think about umbra to umbra connections here. Well, first I should mention that this plot is perfectly fine, as Ignacio has done, because he only selected hottest loops. So this is what he found. That is fine. But somehow, if you can measure the emission in these loops, in this loop, umbra to umbra connections, as well as consider all loops, then you will have, particularly this umbra to umbra connections, this will fall somewhere here. You have strongest magnetic field, but you have least emission. That means the idea, the general idea, and the scaling laws that directly correlate heating with magnetic field, that may not be fundamentally correct. Okay, I think I just spoke about these things. I will go to next slide. If you think about this one connectivity where you have mixed polarity flux, there have been a lot of research investigations. Actually, it was first pointed out by Falcone et al. And Moore et al. But then recently, there have been observations that find that heating in loops is often linked to mixed polarity flux and flux cancellation. And flux cancellation of order of 10^15 to 16 maxwell per second has been found in most of these studies. So one thing you can always point out that irrespective of whether there is mixed polarity or not, if it is only unipolar, the heating will still be according to the picture that I presented and this sketch, through this sketch. Heating will be maximum in these three connections anyway. Although we want to find out, it would be interesting to find out what percentage of these three connectivities and active regions have mixed polarity magnetic flux at least one foot point. And that is what we studied last year together with student Caroline Evans. And this is a high active region, which was also observed by High-C second flight. And we followed this for more than 24 hours again and selected the hottest loops. So we removed warm components following method of Warren et al. From AIA 94, and we followed track their foot points. So we selected line of sight magnetograms using HMI magnetograms, line of sight magnetograms, and made histograms of these foot point flux elements to see whether there is mixed polarity flux or not. This is very important point here. So we took help of, again, magnetic field extrapolation to make sure that the loop foot point that we chose here is actually in the center of the box that we selected. And the box size was selected to be as small as possible to make sure that none of the, not even single pixel of the loop foot point was left out. These are just light curves to find out the behavior of these loops. Okay, these are again those three examples, and here we have this extrapolated loops to verify and adjust the loop foot points, basically the location of these blocks. So we found three categories of loops in this histogram. These are histograms of these foot points, one foot point, second one of the loop. These are three examples of the loops. So in the first category, we found that none of the foot points of the two, of course, there is mixed polarity magnetic flux. So this one is purely unipolar, it has only negative magnetic flux, and this one is purely unipolar, it has only positive magnetic field. The second category, we have both of the loop foot points rooted in mixed polarity magnetic flux. Well, this is small here, but then we made sure that we took 20 PC values above 20 Gauss to make sure that when we consider mixed polarity magnetic flux, it is not within noise. The third category has one foot point unipolar and the second foot point in the mixed polarity magnetic flux. We found that about 60% of the loops that we selected, we had about 23 or 24 loops that we selected in 24 hours. About 60% of the loops have mixed polarity magnetic flux at least at 1 foot. And about 40% of the loops have both feet unipolar. Chet et al. Did a similar study and found that more than 70% of their loops were rooted in mixed polarity magnetic flux. And these numbers may change when DKIST provides observations, or may not. May not change. These numbers may not change. DKIST will obviously provide observation. We also found that loops with both feet unipolar are 15% shorter lived on average than the loops having mixed polarity point flux, but their peak intensity averages were equal. Here I point out some of the points that support the flux cancellation idea. Then I will also discuss briefly points that challenge the flux cancellation idea. Majority of coronal loops show mixed polarity magnetic flux at least at one of their feet, and this supports flux cancellation idea. Any transient coronal transition region heating is most often accompanied with visible flux cancellation in HMI magnetograms if you see in the solar surface. Different sizes of jets are triggered by magnetic flux cancellation. And jet-like structure is also seen at the base of some of coronal loops. Different fine-scale exposure events, for example, found in high sea observations, are seated at mixed polarity magnetic flux, often with visible emergence and or cancellation. In most of the small loops, heating propagates from one end to the other end. Well, this is an image from Bifrost stability simulation, and when we extrapolated the loops of this is from the solar orbiter, from this paper, which is about solar orbital observations of fine scale bright dots in an emerging flux region. And I'm not going to talk much or more about these two papers because that will be a colloquium in itself. So what I want to point out here that we found that in many cases, about 50% of cases in 170 loops that we selected, 170 dots that we found at reconnection site here, intensity propagated from one end to the other end. So this also supports cancellation idea. Now there are some challenges that we point out here. The absence of mixed polarity magnetic flux to the detection limit of HMI, of course, in 40% of the brightest loops suggests that flux cancellation may not be necessary to drive heating in coronal loops. Irrespective of that, magnetoconvection and field strength at both loop feet possibly drive much of the heating. Mixed polarity or cancellation may be just adding some heating to the loops as seen for plumes. I will talk about this later. If flux cancellation takes place at one end of the loop, one should expect asymmetric heating extending from the cancellation side to the other end. This is not commonly seen in typical loops, although I just mentioned that we found in recent observations, there are some indications that loop intensity propagates from one end to the other. For smaller tiny loops, as found in the core of the high sea active region, cancellation as a result of submergence of lower reconnected loops is possible, but Think about typical coronal loops where heating is often symmetric and often starts at the apex of the loops. Flux cancellation may not be important, and this is in line with the fact that solar flares most often start high in the corona, not always, but most often, and probably cannot be claimed to be always driven by magnetic flux cancellation. Further, if reconnection happens in lower atmospheres and the chromosphere, that is where we find for small scale events at least, for typical coronal loops, radiation should probably be efficient to cool it rapidly before reaching to millions of Kelvin. And then you can always argue that there is, due to complex coupling of short and long loops, the energy is rapidly injected can be injected along the long loop. From the cancellation side, then again, one would expect asymmetric heating and unidirectional flow. Something like this structure you expect. But not, I mean, some of the loops are, of course, heated in this way, but this is not that common. Finally, there are other heating mechanisms, wave heating, turbulence heating. They don't require cancellation at the loop pitch. Okay, so this is a summary of part one of my loop heating part, in that we found that there is a systematic difference of the heating in active residual coronal loops on the photospheric magnetic flux at their feet, freedom of convection, and strength of the field together at both of the loop put points determine the amount of heating in a loop. Magnetic flux cancellation, which is often accompanied by emergence, seems to play an important role in heating loops and driving other small-scale explosive events, but there are challenges. This is far from settled. I will talk about plume heating. This work was done by, again, my previous REU student, Alice Villani. Plumes are fountain-like structures, bright in, of course, coronal emission. They have lifetimes of few hours to several days. They exist in both on-disk and off-limb coronal holes and quiet regions. And what are the processes behind heating the plumes that remain mysterious? This is an example of just diagram of how plumes look like. But here we have observations. This is 171 again, and you can see there are many plumes. For example, here there are some plumes. These are plumes here, and plumes are most clearly visible in 171. Therefore, we use 171. This one here. So we can definitely see plumes, but we cannot identify coronal hole that clearly here. Therefore, to find out whether a plume is rooted in a coronal hole or outside coronal hole, we followed the same regions with AIU 211 images. It was proposed by Raufi and Sternberg that jetlets, which are small jets propagating along these plume structures, those feed most of the plumes. And those are driven by magnetic flux cancellation. Here you can see this is the main flux page of the plume, and this positive flux disappears. But at the same time, it has been found in the literature that most plumes are predominantly unipolar. Even in AIA and HMI data used by this, we found that most of plumes are predominantly unipolar. Also, Panesar et al. Showed that jetlets occur at photospheric magnetic network regions with or without plumes. So you have jetlets at multiple places, and some places you have plumes, and some places you don't have plumes, but you have similar jetlet structures that you found. And again, she also found that these are all caused by magnetic flux cancellation. That means because jetlets can happen anywhere in any network page, whether there is a plume or not, we don't know whether that is really fundamental. Wang et al. Found that convergence in magnetic flux at the photospheric base is the mechanism that, of course, is directly correlated to the plume formation. So, for example, this is when magnetic field is strongest, and that is when plume is brightest. They also found no evidence that jetlets systematically correspond to plume formation. There is an indication of mixed polarity flux in some cases, and is expected due to the presence of loop structures. So Wang et al. In different papers also found that there are loop-like structures in the class region, this unipolar, visibly unipolar class regions, and then there is possibility of magnetic reconnection, that is interchange reconnection between the open and those closed field lines. And this is consistent with the interchange reconnection model of plume formation. These were mostly qualitative investigations, those two work. So Ellis basically took it to quantify and find out whether there is a threshold value or magnetic strength that is required to form the plume. For example, you can see this flux patch converging, flux elements are coming close to each other, and of course the filling factor gets close to 1. And then you have the strongest magnetic field, and that is when plume forms. After some time, when the flux starts diverging again, you can see that the plume disappears. Now flux diverges and plume disappears. So there is obviously there is a direct correspondence, but then what is happening when you have convergence? There might be many different mechanisms that could be responsible for plume heating. But then one that Ellis wanted to test was very obvious one, that when you have small flux elements coming close to each other, you have a magnetic field getting stronger, and whether that is something, there is a threshold value that can lead to the formation of these plumes. So for that, she basically calculated cross correlation between the luminosity and magnetic flux, considering different BZ values, starting from 10 Gauss to 20, 30, 100, 200, like that. So this is here a 171 luminosity, this blue dash dotted line. And these are different threshold plots for magnetic flux. I will show you which one matches best, and that is this point here, about 200 Gauss. Okay, so this is just in pictures. You can see that flux converges and plume brightens, and then flux diverges, plume disappears. When the magnetic field is strongest, plume is brightest. So what we found there, that when you take about 250, all pixels above 250 Gauss of BC value, then you have maximum or best correlation between the luminosity, AIU luminosity, and magnetic flux. This is an example plume, and that is in non-coronal hole Coalescence region. The previous one was in coronal hole, so that was a plume in coronal hole region. Here also you find, actually you can see there is a similar pattern. You have magnetic flux convergence, and then plume forms. When the magnetic field is strongest, plume is brightest. And after some time, when magnetic flux starts diverging, the plume disappears. Now, for example, we did the same thing here and found that a different threshold value for this example. She studied 8 plumes that way. Anyway, this is again images from those movies, and the movies I showed you just before. So you have magnetic field strongest here, and you have plume brightest. Then magnetic flux here disperses and plume disappears. In this case, we found all the pixels. When you consider over 350 Gauss, then you have best correlation between the luminosity. So this suggests that, okay, strong magnetic field is important. So we have not found any of the plume formation that doesn't correspond to magnetic flux convergence and divergence when it disappears. But interestingly, we found that there are, at least we found 2 locations where you have similar magnetic flux convergence as you saw just before in the plume, those 2 plumes, one in Quietson and one in coronal hole region. And those 2 have flux, similar flux actually as this one, and this one doesn't form any plume. So what is going on here? We don't know. That means, although, because every plume can be seen to form or correspond to magnetic flux convergence, that is a necessary condition. But that is not sufficient, it seems. These two examples show that flux convergence and a strong magnetic flux or magnetic field at the plume base might be necessary. It is not sufficient to form plume. Again, this has similar values as seen for other plumes, but we don't see plume forming. Okay, so this is summary for our second part of my talk. We found a critical BC value of 200 to 600 Gauss for our sample of 8 coronal plumes. We also found that plumes in quiet regions, which are most likely feet of closed loops, and coronal holes, which are, of course, open field structures, exhibit similar characteristics. A strong base magnetic field is necessary for plume production, but it is not sufficient to trigger plume formation. Other possible triggers for plume evolution include heating by waves or turbulence and hidden mixed polarity magnetic field, etc. Now we looked at iris observations to find out. This has been very puzzling, why some of the similar flux convergence regions form plume and others don't. We wanted to look at, we know that there are some theoretical, at least, views that heating might be driven from low into the atmosphere, chromosphere transition region. So we wanted to see whether there is a difference in the plume and non-plume region in iris slit images and in iris spectra. Magnesium spectra we have analyzed so far, but we are looking into it. This is something we are still working on. And these are 3 examples of plumes, and this is how in switch image 1400 a plume looks like in of course in the transition region. If you remember, or you have looked at iris switch images enough before, then you can steadily remember that there are many of this kind of patches where you don't have plumes. At least we have seen that. So that they are on the sun, you can find this kind of, any network patch has this structure. And I mentioned before, Navdeep Panesar et al. Paper, in that they found that irrespective of whether there is a plume or not, they have network jets. And those are similar to jetlets. So what we have done so far, okay, before that, I'll show you 2 examples here. So this is a flux patch. This is a bigger field of view, so patch is smaller here, but this is a flux patch that has a plume. And this looks like this here in the magnesium slit image. And then there is a similar magnetic flux patch. Of course, we have looked at plots, etc., to find out that they are very similar and they have similar convergence, etc. But this one doesn't have plume. Now we want to compare that, what is difference between these two, and we have a couple of sets of this kind. What is the difference between these two? That one has plume, one doesn't, and whether we can find a difference by investigating iris, magnesium, silicon, and carbon spectra. So we first thing we did was that we averaged all the magnesium 2K profiles and followed in time. We have high cadence data here. So we followed in time to find out if there is any difference between this and this region. And so far, we have not found any differences. Similarly, we also have looked at line of sight magnetic field scatter plot with intensity at K1, K2, and K3 regions. K1, K2V, this is K2R, and this is K3 location of magnesium line. And we have not found any differences there too. Not only this, we also find that this work is done by one of, again, previous student, this is by Esther Chao. And we found that similar to plumes, there are many loops that form due to magnetic flux convergence. So you have this, you can notice that here, this flux is the strongest, magnetic field is strongest here. And that is when the loop forms. And after that, it starts diverging and loop disappears. With time, you can see in the movie that happens very clearly in the same way as happens for the plumes. Now, so flux convergence is also important for some of the loop heatings. We don't know how many. We have not done a large statistics here. for the loop heating so far. But then what is important here is that we also found many other locations where we have similar flux convergence and we expected loop formation, but there was none. So we don't know why some of the areas, flux convergence patches form loop and plume, and some don't, any of them. Whereas we have similar environment, all kinds of environment. We are still looking into it, but this is an interesting question. Okay, so this is my summary of my talk. There is a systematic dependence of the heating in active region coronal loops on the photospheric magnetic flux at their feet, freedom of convection, and the strength of the field together at both of the loop foot points determine the amount of heating in a loop. Magnetic flux cancellation, which is often accompanied by emergence, seems to play an important role in heating loops and driving other fine-scale exposure events. But whether this is essential, that remains far from established. A strong magnetic base magnetic field is necessary for plume production, but it is not sufficient to trigger plume evolution or plume formation. Why do some of the flux converging regions not form plumes, even when these have similar magnetic field as in plume forming regions? And this question is also valid for loop. Why do some of the flux converging regions where you have similar flux convergence as where loop forms, but other places loops don't form? Since some theoretical approaches suggest that heating occurs low down in the solar atmosphere, we plan to use iris spectra, as well as we plan to synthesize bifrost image simulations of network regions and also coronal hole regions to look for differences between plume and non-plume regions. Finally, our observations provide new insights and constraints to future 3D MST models of active regions and quiet sun and coronal hole plumes. Thank you for your attention. I'll take questions.
Thank you very much, Sanjeev, for an exciting presentation. So now it's open for questions. Either raise your hands or just unmute yourself and ask your question. Matthias.
Yeah, hi, Sanjay. Thank you for the very interesting talk. I do have a question regarding this question, whether when you have the mixed polarity at some foot point, whether this should lead to an asymmetric heating of the loop or also a symmetric one. And at least I could think of, I mean, two ways you heat the loop in this case, right? The one is you have really reconnection somewhere low down in this foot point, which produces some hot plasma, which is then through flows filling this loop. And then you would expect to have an asymmetric heating of that loop. The other way I could think of it is when you have these flux cancellation, you very rapidly change the feed line connectivity at that foot point, which you could think of something like a braiding pulse, right? Where you would change, really move the foot points of feed lines around. And this pulse will propagate on an aphanic time scale along the loop and kind of distribute over the loop. And then you could potentially have symmetric if these stresses, which are now distributed along the loop, are just like in the classical braiding picture, are released in the corona through reconnection. Is there any indication which one of the two processes is actually happening on the sun, or is this still a pretty open question?
I think in very high resolution, I'm talking about high cadence here, as well as resolution, of course, spatial resolution. Observations of high C, for example, and also recent solar observations, it seems there are more and more indications of this kind of unidirectional flow and heating propagating or intensity propagation from one end to the other one. But I'm not sure. Think about coarser data. If you don't have really high resolution to capture the second mechanism that you mentioned, that you have braiding and there is a pulse that reconnection drives on the top, and you cannot understand or resolve that in time in the observations, then we will not know whether there is a symmetric heating or it it propagated from one end to the other. So my point is, even in your second case, if you have braiding and one end where you have reconnection, or let's say trigger due to cancellation, whatever starts, if you have very high cadence data, we should be able to see asymmetric heating. So answer to your question is that this is not resolved yet. Yeah, we don't know.
Okay, thank you.
Thank you.
Other questions? Just unmute yourself and ask. I'm not seeing hands raised. Matthias?
Yeah, maybe one other question actually regarding the slide you're showing here, where you have these, concentration of magnetic field at one or both foot points, and then you get a bright loop, and then it disappears. You mentioned in other cases this concentration is happening, but you do not get a brightening. Did you try to investigate whether, there are different ways you can concentrate a foot point, right? You could just have some radial flow which just concentrates it and then disperses, or you could have some additional torsional motions or some motions within the foot point. So there are a lot of different ways you could do this, which go beyond just seeing a concentration. Are there any differences on that scale between these cases where you see heating and the cases where you don't?
No. So they are at same time scales. They are at same intense magnetic field. Strength is very similar, and they're also okay. They have very similar patterns. So if you look at flux convergence only, then you would definitely expect to see. Okay, let me come to this one. Yeah, this is quite some one, but this one. So it has. So if you just look at this movie, and if that is what I was surprised to see first. So I would expect a plume formation, and the time scale, we looked into it a little bit more into details, and we have similar time scales or field strength and everything, and that is what surprises. So we have not found a solution yet, or the reason why one convergence, similar convergence forms plume and other one doesn't. And for loops, it is just few examples that we found. Actually, Esther found 10 examples. But then for loops, it is more common to not see loops when you have convergence. But for plumes, it is more, when you have this kind of convergence at this order of magnitude of magnetic field, then often, most often, you see a plume formation, whether it is quiescent or whether it is non-coronal hole quiescent or it is quiescent or coronal hole, you do see a plume formation with this kind of convergence. So scales, and also this chromospheric thing I mentioned from Iris, we have been looking around, but this is very puzzling. We have not found a solution, a region. What could be causing this kind of behavior?
Yeah, my question was more if perhaps one needs higher resolution to look at kind of something like a substructure in these.
Yeah, so that is
concentrates, maybe some flows which are not resolvable in HMI easily.
I agree with you. So that is what something, other possible trigger mechanisms could be hidden mixed polarity and also plasma flows that we don't resolve in. So, this project, we also want to look at the flows using LCT, local correlation tracking on the photosphere, to see how different it is in one case to the other when you have plume and when you don't have plume, as well as, of course, looking for high resolutions in future with TTS, probably that will be helpful. But at the same time, we are also planning to look in SP, the SOT SP observations. Now, SOT SP can actually provide provide means it was also able to provide before, but now that we don't have FC, SOT can provide high cadence observations of 6 to 7 minutes for 20 arc second to 128 arc second field of view. So we are trying to find out something in there too. But you're right, there might be some unresolved structures of magnetic field and flows that might be responsible for this kind of behavior. And thank you for pointing out that.
Thank you. Any other question? I don't see anyone. Please just unmute and ask if you have any question. Looks like there is no other question. So let's thank our speaker again. Thank you, Sanjeev, for a very nice talk.
Thank you very much.